Let's pick up where we left off with the calculus of parametric equations. And so now that we're working with parametric equations, x equals f of t and y equals g of t, squeezed in up here at the very top of this page. If we're talking about a curve that is defined by these two parametric equations, what we want to do is we want to extend a lot of the same topics, a lot of the same concepts that we had in Calc 1 and Calc 2 into this definition of a curve in parametric form. And so we talked about finding derivatives and looking at equations of tangent lines in a previous video. So now let's talk about finding a couple other applications. Like what if we wanted the area of a parametric curve or under a parametric curve to the x-axis? And so to do that, the first thing we're going to do is we're going to think back to just how did we compute area under a curve that was defined explicitly. So let's take a look. So if we had a curve that looked like this would be the function y equals f of x. Notice here that f of x is greater than or equal to 0. And if we wanted this area underneath this curve to the x-axis, this goes all the way actually back to Calc 1, but also revisited in Calc 2. The area formula, or the area that we derived through Riemann sums, was to find the area by taking the integral from a to b of f of x dx. Okay. Now, we also extended that and said, well, what if the curve was instead a function of y? We called it g of y. Well, if that were the case, we could find the area from the curve. We kind of tilted, and I'm even tilting my screen sideways here to draw my area lines. And we just said we could find that area simply by constructing our rectangles for the Riemann sum along the y-axis. We could find that area as the integral from c to d of g of y and integrate with respect to y. So we're going to just extend those exact concepts and talk about, well, what if that same curve was defined parametrically? And if that same curve was defined parametrically, the same concepts can apply. So let's talk about that. So let's get in here. Okay, so we know that the area under a curve for y equals f of x, as long as f of x is greater than 0, is, as we just said, the integral from a to b of f of x dx. So now we can say if that same curve is traced out one time by a parameterization on some parameterization, we'll say from t runs from alpha to beta, then we can actually calculate the area just simply using substitution. And we end up finding that the area is actually the integral from t equals alpha to t equals beta of y dx, which is, if we actually make those substitutions, that's g of t times f prime of t dt. And we can take that, so we're literally just making substitutions here. We're saying, okay, so we're just going to say that's y dx dt, but we want to integrate with respect to t, so that turns into our little dx. Okay, extend the same idea over into the other orientation, and we can even say that take that exact same area that we talked about along the y-axis, now the integral from c to d of g of y dt, and think of the curve now being defined as a parameterization defined by two parametric equations from alpha to beta. And we can say the same thing. We can say, check that out. Look at that. Through substitution, that's going to give me x dy, or the integral from alpha to beta of f prime of t, or f of t times g prime of t dt. Okay, so we're literally putting together two different concepts here, substitution and what we already know about area. So let's utilize these formulas. Let's take a look at an example. So if we were to want to find the area under a curve, under the curve defined by x equals 10 times theta minus sine of theta, so our parameter here is actually theta instead of t, and y equals 10 times 1 minus cosine of theta from 0 to 2 pi. And by the way, this is the parameterization of what's called a cycloid. And so a cycloid would be the pathway that is traced out on a point. And so here's just a little image that I grabbed so that you could see what's happening here. A cycloid is the path. If you take a point on a wheel and you rotate the wheel, you get this pathway. The first curve is from 0 to 2 pi. If you keep going, if the wheel continues to rotate, every 2 pi. Every time you go through one circumference of the wheel, you get this, this curve, and it continues on and on. So we're only going to go across the first from 0 to 2 pi, and let's figure out what would be the area of that cycloid from 0 to 2 pi. So this first point right here is when t equals 0, and this is when t equals 2 pi, when it hits right here, here and here. And we want to know what is the area under this curve that gets traced out by that parameterization, where x is actually equal to 10 theta minus, oh, I said t here, we'll change that to thetas. 10 times theta minus sine of theta, and y is equal to 10 times 1 minus the cosine of theta is what traces out this curve. I wrote t's here for the parameterization, but I'm going to change that because the parameterization is actually, we're using the parameter here in terms of theta. So from 0 to 2 pi. So if I want that area, what I would be looking at in, let's just suppose that had been an explicitly defined function. Well, we would think of, okay, that area, if it had been defined explicitly, that area would be the integral from x equals a to x equals b of y dx. Well, let's write it this way first. It would be f of x, some capital F of x, dx, where y equals capital F of x. So we could actually write that as that would be the integral from x equals a to x equals b of y dx. Okay? That gives me my start as to, okay, what am I going to do here? So I'm going to extend that. We've just talked about how that actually is the pathway of a cycloid, the parameterization of a cycloid, the path traced out by a circle or a wheel as we roll that circle or wheel across the ground, letting theta equals 0 or t equals 0 be the first point, the origin on the xy plane. And so we actually know that this is getting traced out, just by the definition here, this is getting traced out one time, and the direction of motion does go in this order. We're tracing that pathway out, increasing order of the parameter, and so we can make those extensions and we can say, well, that would be exactly the same as looking at the integral from, instead of x equals a to x equals b, let's do the substitution. This is going to be from theta equals 0 to theta equals 2 pi of y dx in terms of the parameter, or the integral from 0 to 2 pi of f prime of theta, f of theta, g prime of theta, d theta. And we can make those substitutions because we do have the parameterization of the same curve that we're looking for the area here, and it's traced out one time from 0 to 2 pi. Okay, all right, so let's do it. So now we're ready to find it. So, by the way, just one other little connection, just through our definition, the way we define these parameters, this is your f of theta, and this is your g of theta. As I did that, guys, I just realized I made a mistake. I have y dx, and then I wrote g dy. So let's get in there and clean that up. So as we said, y is actually g of theta f prime of theta d theta. All right. So now we have our formula. Now we just need to figure it out. So we're taking y dx. So we're taking the derivative of x. We're going to have y times the derivative of x. And so let's do that up here so we have those before we do the substitution. So our dx d theta here is actually going to be 10 times 1 minus cosine of theta. And so we can plug that in for f prime of theta Let's see if we can get it all on the same screen here. So this is going to be the integral from 0 to 2 pi of 10 y, 10 times 1 minus the cosine of theta, times, turns out, the derivative of f here, dx, is actually 10 times 1 minus the cosine of theta as well, d theta. And now we just have to do some integration. So we could also practice some integration here. So we got the integral from 0 to 2 pi of 100 times 1 minus the cosine of theta, quantity squared d theta. So we'll expand that out. So that's going to be the integral from 0 to 2 pi of 100, 1 minus 2 cosine of theta plus the cosine squared of theta d theta. Continuing this on, we're going to end up with the integral. I'm going to do one more step before I actually integrate because I see that I want to apply that half angle theorem there on that, reduce that power. So I've got 100 times 1 minus 2 cosine of theta plus 1 plus cosine of 2 theta over 2 d theta, using a little integration strategy right there, little identity, going back, practicing on some of those integration strategies here as we go back into some applications of integration just with parameterizations. And now we can actually integrate, well, let's write one more step. 0 to 2 pi, we still have 100. I'm going to go ahead and collect those and make that 3 halves, 1 plus the 1 half, minus 2 cosine of theta plus 1 half cosine of 2 theta d theta. And now let's actually integrate. So we're going to have 100, 3 halves theta, minus 2 sine of theta, plus 1/4 sine of 2 theta, all evaluated from 0 to 2 pi. And check that out. When we actually plug that in, we end up with 100 times 3 halves times 2 pi. The rest actually zeroes out, plugging in the 2 pi. And of course, when we plug in 0, that zeroes out as well. And so our answer here is actually 300. 150 times 2 pi, or 300 pi. And that represents the area under the first, I guess we could call it bubble, of the cycloid. All right, so let's zoom out here and get it all back on the same page. I know it's kind of small, but there we go. That's what we're looking at. So we're saying, all right, we still trying to find area, but now that we're trying to find area, if we have a curve that is, instead of defined explicitly as a function of x, if we could look at its parameterization and apply a lot of the same rules, a lot of the same concepts about area, we can do that through substitution and looking at area. So there we go. So taking the integral in terms of theta rather than in terms of x. Okay, so now we've got it all on the same screen. If you want to pause that, check that out. But let's head back and think about another concept. So I have another example, but I'm going to save that for a class session. So this example, finding the area between the curve and the x-axis in a very similar way, except we're going to be doing it in terms of thinking about it in terms of the way we did when we did things that were oriented the opposite direction of, instead of f of x, we'll be thinking about g of y. Okay, so what about arc lengths, right? What about arc lengths? And it turns out we can take that same application and in a very similar way, go through a little proof here and do a substitution as long as our parameterization traces the curve out one time as the parameter increases. And so just again, remembering what is the arc length of a curve, and we showed that the arc length of a curve is defined, if we have a curve y equals f of x, and we want the arc length of that curve. We did a whole calculation, broke that into line segments, and came up with, used our distance formula, came up with a formula that said if we actually want the arc length of this curve, so we want to know what is the length of this curve from A to B, the actual arc length formula is the integral from A to B. We called it ds, and we showed that ds was actually equal to the square root of 1 plus dy dx quantity squared with respect to x. Now we extended that. We also talked about how we could do that along the y-axis and integrate with respect to y back in, I think that was chapter 8 actually. But here we're talking about just in general, arc length, integral from A to B of this 1 plus dy dx. But we showed earlier in this section that to find the derivative dy dx, if you have a parameterization, that's the same as dy dt over dx dt. So we can make those substitutions here. Of course, if we're making that substitution, looking at it in terms of dt instead of dx, we also have this substitution that we plug in. Through some algebra, we can show that that actual arc length is equal to the integral from t equals alpha to beta. Now again, we have to be kind of specific. I jumped over this middle paragraph and kind of just glossed over it and said as long as our parameterization we get traced out one time. So we do have to say that. We have to say we're traced out one time, because it turns out with parameterizations you can actually go around a curve multiple times as you increase the parameter. Think of the circle, for instance. You trace a circle out once from 0 to 2 pi of the parameter, but if you continue and you allow the parameter to increase, you'll continue to just cycle around the circle. So you have to make sure you're traced out one time by a parameterization from alpha to beta. And there is this other piece that dx, the f prime of t, is actually greater than 0. So there is this other little piece here that we are talking about. That means that it's actually traversed exactly one time from left to right as t increases from alpha to beta. Okay? So f of alpha equals a and f of beta equals b. And so then we can calculate that. Okay. Let's go just down to the actual formula. So that was a rough proof. It was a typed up proof to go for speed here and focus more on the examples in the videos. But here we go. So here's the arc length of a parametric curve if a curve is described by the parameterization. So as we talked about just a second ago, we have a parameterization x equals f of t and y equals g of t from alpha to beta, where the two derivatives are continuous functions from alpha to beta, and the curve is traversed exactly one time as the parameter increases from alpha to beta. Okay? Then the arc length formula can be found. The arc length can be found through this formula. So take the integral from t equals alpha to t equals beta of the square root of dx dt plus dy dt and integrate with respect to t. So let's take a look. So what if we had, let's go to that circle example that I just mentioned. There we go. So let's take a look at this circle example. So if we have a circle of radius r, if we have a circle of radius r, and this was from the previous section, if we have a circle of radius r, its actual parameterization can be written as x equals r cosine of theta and y equals r sine of theta. We will trace it out one time from 0 to 2 pi. So that's the parameterization. And let's find the arc length and show that it gives us that circumference formula. So if we have a circle of radius r in the xy plane, circle of radius r, the parameterization can be written as x equals r cosine. And I will use theta because we're talking about circles, and so it does make sense. We could say t if we wanted to, but I'm going to use theta. X equals r cosine of theta, and y equals r sine of theta on theta from 0 to 2 pi. Now, if we were to continue and go from 0 to 4 pi, for instance, that would actually cycle through this 2 times, okay? And if we were to ask to find the arc length from 0 to 4 pi, we would actually get twice the circumference because we would be tracing through the curve 2 different times. So we can show that once we get through here, but let's actually find the arc length. So to apply the arc length formula, and I'm just going to rewrite it here. This does meet the criteria. The arc length formula, since this curve will be traced out, it is a circle, and so we would be tracing it out one time. We are increasing the parameter with the direction of motion. We could plot some points. I'm going to skip that part. That's from a previous section. We could plot some points, but we could see that this is where theta equals 0, theta equals pi over 2. We're going to cycle all the way around and get back here again when theta equals 2 pi. So we will have cycled once through this from 0 to 2 pi. So the integral is going to be from 0 for arc length is going to be from theta, the parameter, equals 0 to theta equals 2 pi. It's going to be the square root of dx dt squared plus dy dt squared with respect to t. Now, I wrote that from the formula with the t's, but these are thetas. Since we have changed the parameter, we're now talking in terms of theta. So I will write these in terms of theta in the formula. Okay, so all we have to do now is actually find those derivatives. So dx d theta, take the derivative here, that's going to be negative r sine of theta. Take the derivative of y, dy d theta is going to be r cosine of theta. Plug those into the formula here, and my arc length is going to be the integral from 0 to 2 pi of the square root of negative r sine of theta squared plus r cosine of theta quantity squared with respect to theta. Now check out what happens here. So now this is just the integral from 0 to 2 pi of the square root of r squared sine squared of theta plus r squared cosine squared of theta d theta. But that's the same as just r squared times sine squared theta plus cosine squared theta, which of course that is just 1. So what we're looking at here is the integral from 0 to 2 pi of just the square root of r squared d theta. And r is a radius, so it's positive. So the square root of r squared is just the integral from 0 to 2 pi of r d theta. And that's just a constant. So like 5, like if the radius was 5, that would just be 5. So this would just be r times theta evaluated from 0 to 2 pi, which is just r times 2 pi minus 0, or 2 pi times the radius. And that is the arc length. Check it out. That is the circumference of a circle. Circumference is 2 pi times the radius. It's pretty cool. That's exciting. That deserves some rainbow fireworks. Okay, so we've just proven using an arc length formula, the formula for the circumference of a circle. And so that's simply using a parameterization and a little bit of arc length formula and a little bit of calculus with the arc length formula and some integration here. And we can show that 2 pi r. Now I mentioned at the beginning that we do want to be careful. I'm going to go ahead and zoom out so we can get it all on the same page. I mentioned at the beginning that the formula dictates that you have to trace the curve one time as the parameter increases from alpha to beta, which is true on this case. We're tracing it out one time. If we were to simply say, just a kind of a little side note here. Side note, if we were to simply say, let's go from 0 to 4 pi, right? 0 to 4 pi would actually traces out the circle that would just go one more time around. So that traces out the circle 2 times, by the way. And if you were to integrate this exact same thing from 0 to 4 pi, if you were to think about, well, what would that make the arc length? The only thing that's going to change from 0 to 4 pi, you're still going to have the exact same integral. So you're still going to have that same integral, blah, 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 d theta. What's going to end up happening is you're going to have r theta evaluated from 0 to 4 pi. And notice what you get. You get r times 4 pi, or 2 times 2 pi r, twice 2 times around the circle. Okay? This arc length, I mean, calculus is really good at what it does, right? Like if we tell this integral that we want the parameter to increase from 0 to 4 pi, what we're telling it is we want the parameterization to cycle through the circle 2 full times. So the actual arc length that would be traced out there should be twice the circumference. Okay? So it will generate back exactly what it's being asked to do. Okay? It will just take that parameterization and calculate arc length 2 times around and give us back 4 pi times the radius, okay? Twice around the circle. So that's that piece about you want to make sure you're traced out one time. If you happen to increase the parameter and go more than one time around the curve, well, then you're going to get the arc length of whatever you've asked the integral to calculate. Okay, all right, so that summarizes up the majority of the applications. There is one more. We'll go ahead and do this second example in a class session. There is one more application, surface area. And I'm just going to briefly talk about it here. I'm not going to go through an example. It's just continuing. Once we have arc length, we can easily apply it to surface area. And so if we wanted to think about, rather than just the arc length of a curve, if we wanted to revolve a curve around an x or a y axis and look at surface area, we can actually use the same formulas that we did back in, as long as we have the same criteria, right? We have a parameterization that gets traced out one time as the parameter increases, t increases from alpha to beta. We can use these same surface area formulas where our ds is now defined in terms of the parameterization. So we can extend this. So this is extending the idea, extends the surface area formulas. Now that we have a description for ds, it extends the surface area formulas to parameterizations. Parameterized curves. Okay. So another extension, but I wanted to focus more on areas and arc lengths. These particular integrals can get quite complicated, and a lot of times we just set them up, just plug into the formula and set them up, and then maybe use numeric integration if needed to figure out what the actual approximation is for the surface area. Okay. All right, so that wraps up the applications of parameterizations of parametric curves applied to calculus. And now we'll talk about a specific type of parameterization and talk about some more examples during the class sessions.